Okay, so we'll go ahead and start now. So today we have three topics to finish. We have to talk about the geometry or the conformation that's required for an E2 reaction to occur. We need to talk about how we can prepare alkynes by a special type of E2 reaction. And then we're going to talk about looking at a specific set of reaction conditions and deciding when substitution will occur and when elimination would occur. So for the E2 reaction to take place, since we are forming and breaking all of the bonds at the same time, we have to have a specific geometry in order for the orbitals to overlap properly for this reaction to occur. Right? We're breaking a carbon-hydrogen bond and a carbon-halogen bond at the same time as forming a pi bond. And so in order for the orbitals to overlap to generate that pi bond, we have to have that carbon-hydrogen bond and that carbon-halogen bond in the same plane. Coplanar means in the same plane. So there's two ways that you could have the carbon-hydrogen and the carbon-halogen bond in the same plane. We could have what's known as a syn-periplanar arrangement. This is an eclipsing conformation. And the prefix peri just means almost or approximately. And what that refers to is the fact that they don't have to be perfectly planar in order for those orbitals to overlap. If they're off by a few degrees, it's still okay. So syn-periplanar means that we have either this eclipsing conformation or a conformation that's very close to that eclipsing conformation. And then the other arrangement we could have is the anti-periplanar arrangement, where you see that the beta hydrogen is anti to our leaving group, and we have a staggered conformation. Okay? So both of these conformations are possible. Which one do you think would be preferred? Claire? Yes, there's less strain. The term we would use is torsional strain in this case. We have a substantial torsional strain in the eclipsed conformation, and the staggered conformation is free of that torsional strain. So we would expect that the anti-periplanar geometry would be favored for an E2 reaction. And that, in fact, is the case. There's another reason for this preference that is shown on this figure. Our base is electron rich, and our leaving group is electron rich. And if we performed an E2 reaction from a syn-periplanar conformation, we would have to bring our electron-rich base close in space to our electron-rich leaving group. And there would be electrostatic repulsion there. That would cost us some energy to try to do that. Whereas in the anti-periplanar conformation, the leaving group and the base are far apart, so we don't have the electrostatic repulsion. So for those two reasons, lower energy conformation and keeping the two electron-rich species far apart, the anti-periplanar geometry is favored. Question?
If, say, you had the conformation on the right, but then the base attached the hydrogen that's on the bottom, would that just be counted as close enough to an anti-periplanar?
Nope. No, it has to be just a few degrees off. If it goes down here, that's going to be 120 degrees off. And so the orbitals would not overlap well enough to be able to form the pi bond if you tried to deprotonate that one. Okay, so that's the issue is you deprotonate the hydrogen from the spot that triggers the overlapping of the bonds, overlapping of the orbitals to make the pi bonds simultaneous to the deprotonation. Okay, and that can only happen if it is syn or anti-periplanar. And when we say peri, we're talking about, plus or minus 10 degrees or less, probably. Okay, other questions? Yeah, so if we look in the board, it might be easier to see. It's the plane of the board if we're looking at the structures that are in the board. And up here, we're just looking at 4 atoms, the hydrogen, the carbon, and the halogen, and it's the plane defined by those 4 atoms. Okay, so all 4 of those atoms would have to be in a plane. So here, that plane would be roughly coming out at you. It's angled a little bit, but and then the same thing here. It's essentially just coming out at you of the screen. Yes?
So did you say earlier that the hydrogen has to be in line so that its lone pair is close to the orbital?
So there's no lone pair on the hydrogen, but I think what you're referring to is that when you break the carbon-hydrogen bond, the electrons in that bond that's breaking are being used to form the pi bond. Yeah, so in order for the electrons in that carbon-hydrogen bond that is breaking to be used to form a pi bond in a one-step process, that bond has to be aligned with the bond that is breaking when for the leaving group. So that's the requirement there. Other questions? So where this really has an impact is when we are performing E2 reactions with cyclic alkyl halides, such as cyclohexanes that have halogens attached. So let's take a look at chlorocyclohexane, and we draw that in our chair conformation. We learned how to draw chair conformations for exam 1. Hopefully you have not forgotten this skill, because you do have to remember things in this class. So here's chlorocyclohexane. I'm going to draw in the hydrogens on the beta carbons, because those are the ones that are relevant to an E2 reaction. Are there any beta hydrogens that are anti to our chloride leaving group? Okay, I see a shake of the head, and that's correct. If you have your chlorine, your leaving group equatorial, the atoms that are anti are this carbon and that carbon. Right? You don't have any anti-beta hydrogens. Your beta hydrogens are all gauche. Remember the term gauche. So you cannot perform an elimination, an E2 reaction, when you have the chloride equatorial. However, it's easy to perform ring flipping. Ring flipping occurs rapidly at room temperature. And so we can have a ring flip putting our leaving group in an axial position. The arrows I've drawn indicate that this chair is higher in energy than that chair. So we're going to have less of it, probably 5% or less at equilibrium. But that doesn't matter. As long as we can access this chair, we have our leaving group in an axial position. And now we have 2 beta hydrogens that are anti to our axial leaving group, both of which are also axial on adjacent carbons. In this case, they're equivalent to each other. So we can deprotonate either one. It doesn't matter. And we can obtain cyclohexene. So what we learn is that to perform an E2 reaction on a cyclohexyl halide, we have to have that halide in the axial position and have at least 1 beta hydrogen in an axial position in order for the E2 reaction to occur. Questions? So let's look at, yes, go ahead. We will see. It can be the case. So how often, I guess, would depend on who's writing the exam and what kind of questions they're putting on it. But yeah, it certainly can be the case, as we'll see in a moment. Yes, Claire. It's not even syn. If it were syn, it would have to be eclipsing. Right? This is a staggered conformation, but it's gauche. Remember, we had Anti was where we have a 180-degree dihedral angle, and gauche is where we have a 60-degree dihedral angle. So if we look at these hydrogens, if we make a Newman projection down either of these carbon-carbon bonds that involve the chloride, if we make those Newman projections, we would find that our hydrogens are gauche to the chlorine, and the carbons are anti. Right? The carbons are not being deprotonated, so we don't have a hydrogen anti. The hydrogens are all gauche when we have the leaving group in an equatorial position. So let's look at a disubstituted cyclohexane. Let's put a methyl group on our cyclohexane in addition to a chlorine. And let's see, I think I'm going to draw this a little differently. So actually, let's put the methyl group here, axial. Okay. So this is cis 1-chloro-2-methyl cyclohexane. We now have a methyl group, and it's cis. It's pointing in the same direction as our chloride. They're both pointing up in this case. And we'll go ahead and draw our beta hydrogens. I drew this too close to the one above. Sorry about that. Okay. Can we perform the E2 reaction from this chair conformation? Nope. We've got our chloride equatorial, so we have to perform a ring flip. So I'm going to draw it a little bit lower on the board so we don't bump into the one I drew above. Okay, so we do the ring flip. That chlorine goes from equatorial to axial. Methyl group goes from axial to equatorial. And we'll go ahead and draw in the alpha and beta hydrogens. Okay. Which of these two chairs would be lower in energy? The left or the right? Yes, Morgan? Yes, it would be the one on the right. So the question basically asked, what's bigger, a methyl group or a chlorine? That's not necessarily a straightforward question to answer because chlorine is a bigger atom than carbon. But because the methyl group has the 3 hydrogens pointing out in different directions, the methyl group is bigger. The A value for the methyl group, for the amount of energy it costs to have it axial, I think is 1.7. To have a chlorine axial, it's less than 1. It's about 0.6, if I remember correctly. So indeed, the one on the right is going to be lower in energy. And this one does have our chlorine axial. Do we have any beta hydrogens that are axial? Okay. We have 2 beta hydrogens that are axial. I'll label them as HA and HB. So which one would we deprotonate to make the major product of this E2 reaction? A or B? Yes. HA, why is that? Yes. So if we look at it, if we deprotonate HA, then we would make a tri-substituted alkene because this methyl group would be a substituent on the alkene. If we deprotonate HB, we would make a di-substituted alkene. This methyl group would not be a substituent on the alkene. So Zaitsev's rule tells us that the major product would come from deprotonating HA. Okay, so we deprotonate HA, displace our leaving group, and we get this tri-substituted alkene as our major product. Any questions? Okay, so now let's look at the trans diastereomer. Here we have the cis diastereomer, but let's draw the trans. Okay, now our chloride is pointing down and our methyl group is pointing up. Okay. So this chair has our leaving group equatorial, so we know that that's not the one that we can perform the E2 reaction from. So we have to do the ring flip, putting our chlorine down an axial. Methyl group is going up an axial, and we draw in our beta hydrogens. Okay. The way I drew those equilibrium arrows shows us that the chair on the left is lower in energy than the chair on the right, because here we have both groups equatorial. On the right, we have both groups axial. So you're going to have probably less than 1% of this chair on the right at equilibrium, but that's enough. As long as you have any amount of this chair, then you can still have the E2 reaction proceed. Okay? How many beta hydrogens do we have that are anti to our leaving group? Just one. Okay? Only this one right here. The beta hydrogen on this carbon is gauche. We have a methyl group that is anti. So there's no way to deprotonate this beta hydrogen. So in this case, we deprotonate the beta hydrogen on the less substituted carbon because that's our only option. And what that gives us is a di-substituted alkene. And that's the only product we get because we cannot form the tri-substituted alkene because the stereochemistry prevents that beta hydrogen from being anti to the leaving group. Question? Yes. Yes. So when you have a chair and you have groups on adjacent carbons and one's axial and one's equatorial, then those are going to be gauche to each other. If they're both equatorial, they're also going to be gauche. They'll only be anti if they're both axial. Okay. All right. So we have to look at the stereochemistry of our cyclohexyl halides, and we have to look at both chair conformations. We have to draw the chair where the leaving group is axial, and then we have to look at the neighboring carbons to see if one or both of those neighboring carbons has a beta hydrogen that's also axial that allows this anti-periplanar conformation to exist. Okay, so in some cases, such as the one on this the board over here on my left, on your right, in some cases, the product predicted by Zaitsev's rule is not accessible. Any questions? Okay, so let's talk about making alkynes. So alkynes are related to alkenes. We have carbon-carbon multiple bonds. We have triple bonds in alkynes, whereas we have double bonds in alkenes. And so we can prepare alkynes by E2 reactions, but they're special E2 reactions because we need to form 2 pi bonds. We have to perform 2 eliminations. So we call these reactions double dehydrohalogenations. That's kind of a mouthful, but that just means that we are performing 2 consecutive E2 reactions, 2 consecutive dehydrohalogenations to make our alkyne. And so we're required to have a dihalide, not just a monohalide, but a dihalide in order to produce an alkyne. And there's 2 possible types of dihalides that we could use. We could have our halides on adjacent carbons and have each of those carbons contain a hydrogen. And that would be referred to as a vicinal dihalide. The term vicinal means adjacent. So a vicinal dihalide has those halides on adjacent carbons. We could also have the halides on the same carbon as long as we had 2 beta hydrogens on the neighboring carbon. And this would be referred to as a geminal dihalide, where the term geminal refers to on the same carbon. So I'll show you what these reactions would look like, starting with a vicinal dihalide. As I'll explain in a moment, we need a stronger base than usual for a double dehydrohalogenation. So NaNH2, also known as sodium amide, the conjugate base of ammonia. This is a very strong base. Ammonia has a pKa of about 35. So this is a super strong base. It will deprotonate a beta hydrogen. And that gives us an intermediate. That intermediate is a vinyl halide. Okay. And vinyl halides are unreactive in substitution reactions. They're also unreactive in E2 reactions with normal bases, with the bases we've seen so far. But if we use an extra strong base, a vinyl halide will never do substitution, but it can do elimination, where we can perform the second E2 reaction and generate our alkyne. Okay? And we're forming ammonia. I'm not drawing the byproducts, but we're getting ammonia. That's our conjugate acid of NH2. Okay? And notice that because this intermediate vinyl halide is planar, we automatically have that anti-periplanar conformation for generating the product. Okay? So the reason why we need this extra strong base in this case is in the vinyl halide, the carbon-hydrogen and the carbon-halogen bonds are shorter and stronger than they are in the alkyl halide that we start with. So we're breaking shorter bonds that are stronger bonds in this step here, and so we need a stronger base in order for that to be possible. Amide or NH2 minus is the most common stronger base. We'll show you another one that's possible in a moment, but I'm going to go ahead and draw what it would look like if we used the geminal dihalide in this reaction. So if we have the geminal dihalide, we're removing the beta hydrogens from the same carbons. So we generate our vinyl halide intermediate. Sorry. We form our vinyl halide intermediate, and then this time we deprotonate a second time from the same carbon, forming our alkyne. Okay? So geminal dihalides, vicinal dihalides, either will allow you to form an alkyne via a double dehydrohalogenation as long as you are using a strong enough base. So here are a couple of examples that the book shows us of this reaction. And you'll notice that in the second example, so two things you'll notice. Number one, 2 equivalents of the base are required for this reaction. So you have to specify 2 equivalents, meaning if you have 1 mole of your dihalide, you need 2 moles of your base in order for this reaction to occur. If you only had 1 equivalent of your base, what would your product be? It would be the vinyl halide, right? So if you didn't specify, we would assume that you were using 1 equivalent and you would only get the vinyl halide in that case. Another thing you notice from this slide is that we can use potassium tert-butoxide as the base as long as we're using DMSO as our solvent. Okay? The reason for that is that all polar aprotic solvents are not created equally. Polar aprotic solvents solvate cations but not anions, and some of them are more effective at that than others. So DMSO happens to be the best one that we know for solvating cations really, really well. So it's going to get that potassium cation away from the tert-butoxide anion, and then it's not going to solvate the anion. So by effectively solvating the cation and not solvating the anion, our tert-butoxide is as basic as possible in DMSO. Its basicity will be slightly lower in other polar aprotic solvents. And so to have the maximum basicity of tert-butoxide, to be able to perform a double dehydrohalogenation, we have to use DMSO. So if you were asked to provide reagents for a double dehydrohalogenation on an exam and you chose to use tert-butoxide, you'd have to show two equivalents, and you'd have to do that anyway if you were using NaNH2, but you would also have to show DMSO as your solvent, because otherwise you'd get stuck at that intermediate vinyl halide. Okay? Questions about double dehydrohalogenations? Okay, so they're effective at making alkynes, and we'll talk, alkynes are very useful compounds. We'll talk about their uses later on in the semester. All right, so now what we need to do is we need to talk about how we can predict which reaction will occur. So when we have a choice between substitution and elimination, how do we know which reaction will take place? Well, there's a few generalizations that we can use that will help us in this way to figure these things out. The first one is strong nucleophiles that are weak bases favor substitution. Okay? So, what is a strong nucleophile that is a weak base? Who can raise their hand and tell us something that fits in that category? Yes, please. Okay, so iodide. It's negatively charged, so it's a strong nucleophile, but it is a weak base. It's a very large anion. Its conjugate acid is a strong acid. We could put the other halide ions in this same category. Okay. Anything else that fits in this category? Any of the other nucleophiles we've seen? Yes, Morgan. Cyanide, yep. Conjugate acid is a weak acid, so this is a weak base. It's a weaker base than hydroxide. Right, so any negatively charged species that are weaker bases than hydroxide, SH minus, N3 minus, acetate. And then we have our one neutral nucleophile that is strong. What's that? Okay, ammonia, NH3. Strong nucleophile, weak base. So all of these species are strong nucleophiles and they are weak bases. Because they are weak bases, E2 is not possible. And so the only type of elimination you could have with these species would be E1. And we know, we learned on Monday, E1 is not a very good reaction. Usually we're not trying to perform an E1 reaction. But with tertiary alkyl halides, we would see E1. So if we reacted these compounds with a tertiary alkyl halide, we would get mixtures of substitution and elimination because we'd see SN1 and E1. But if it's not a tertiary alkyl halide, it would always be substitution if we're using a strong nucleophile that's a weak base. So that's a helpful generalization that can help us understand or predict what's going to happen in a given reaction. Okay, questions? All right, so the next generalization we'll make, bulky bases that are weak nucleophiles favor elimination. Okay. What is our, when we think of a bulky base, what do we think of right off the bat? Okay, terbutoxide is what we think of. Okay, so it's usually potassium terbutoxide. It doesn't have to be. It can be sodium or lithium, but this is our most common one that is a bulky base and is therefore a weak nucleophile. Okay, so I actually should say bulky bases are weak nucleophiles. It's not that are, because there's no bulky bases that aren't weak nucleophiles, right? They're automatically weak nucleophiles. So bulky bases are weak nucleophiles, and they favor elimination. And then on Monday, we learned two additional bulky bases, DBN and DBU. So we could put those in this category as well. Okay. So these bases are not going to undergo substitution because they're too big. And so we're always going to see elimination, except, I shouldn't have said always, so I should have said we'll see elimination except in one case. There's only one type of alkyl halide that will undergo substitution with terbutoxide. Can anyone tell me what that is? I mentioned it last night when we were doing our Zoom review, if you were there. There's one type of alkyl halide that is our least hindered type of alkyl halide that has no beta hydrogens. What was that? Yes. You're correct. Your guesses are correct. So if you have a methyl halide, iodomethane, bromomethane, our least hindered alkyl halide, you can't get less hindered than that. And there are no beta hydrogens. So the only possibility of a reaction is substitution. Okay, so that's the only time. If it's a methyl halide, you would see substitution. All other cases, then you'll see elimination. Any questions? Okay, and then our third point, third generalization, tertiary alkyl halides are prone to eliminate. Tertiary alkyl halides cannot undergo SN2. And we know that SN1 is much slower than SN2, so the only possible substitution with tertiary alkyl halides is SN1, but SN1 comes along with E1. So if you have a tertiary alkyl halide, you know you're going to have elimination. You're either going to have a clean E2 reaction, or if you're using something that is a weak base, you're going to have a mixture of E1 and SN1. Okay? So these three generalizations can help us predict the outcomes of reactions. Questions? Yes? SN1. Because we know that SN1 and E1 always come together. So if you're going to have an SN1 reaction, you're going to have a competitive E1 reaction occurring at the same time. So the only circumstance that you'll have substitution with tertiary alkyl halides is if it's a weak base, and then it'll have a mixture of E1 and SN1. So you'll always see elimination. In the one case, you'll see a mixture of elimination and substitution. So the book has some tables that are helpful. These tables are organized according to the type of alkyl halide, and they show the different outcomes of the reactions of the different alkyl halides. And we just mentioned that tertiary alkyl halides are prone to eliminate. So if you have a strong base, doesn't matter if it's a strong or weak nucleophile, if you have a strong base in a tertiary alkyl halide, you know it's going to be an E2 reaction. If you have a weak base in a tertiary alkyl halide, you know you're going to get a mixture of SN1 and E1. Okay? On the other side of the spectrum, your primary alkyl halides are going to prefer substitution. Or I should say they're going to prefer or only react by the bimolecular mechanisms, right? They're only going to be SN2 or E2 because we can't form carbocations. And we know that substitution is faster with less substituted alkyl halides, whereas elimination is faster with more substituted alkyl halides. So we know that substitution would be preferred to elimination with a primary alkyl halide. Okay? So what we see here in the table, we have this strong base, strong nucleophile. We only get SN2. The way to get E2 is to use our bulky base that cannot undergo SN2 unless it's a methyl halide. Okay? So primary alkyl halides normally substitute, but you can get E2 if you use a strong base that is bulky. Okay? And then we go to the next table, the secondary alkyl halides. This is where we have the most possibilities because the relative rates of the SN2 and the E2 reaction are intermediate with secondary alkyl halides. Those rate trends cross at the secondary alkyl halide, and so you get mixtures of SN2 and E2 if you were using something that is a strong base and a strong nucleophile. Okay, and we see that here. So we see that if we want only elimination, we would want to use a strong bulky base. And then if we were using a weak base, weak nucleophile, as is the case with the tertiary alkyl halides, we would get the mixture of SN1 and E1. Okay? So these tables have useful information. In my opinion, that same information is collected in a more concise fashion in this flow chart that is shown here. And you have access to this flow chart on Learning Suite. It's called the 351 mechanism chart. So you can look at that under the handouts tab and take a look at it. So to use this chart, we have to be able to do three things. We have to be able to decide if something is a methyl, primary, secondary, or tertiary alkyl halide. So we've got to classify our alkyl halide. We've got to be able to classify our reagent as either a strong or a weak base. And we have to be able to classify our reagent as a strong or a weak nucleophile. Okay? If we can do those three things, we can use this flow chart and predict the outcomes of the reactions. Up at the top, we're reminded that vinyl and aryl halides will not participate in these reactions. Now, I know we just learned that vinyl halides will undergo E2 reactions if you use a super strong base. Okay, so if you have your NH2 minus or your terbutoxide and DMSO, yes, I know a vinyl halide will undergo E2, but that's the only reaction it'll undergo. Other than that, no reaction for these species. Okay, so if we determine that it's an alkyl halide and not an aryl or a vinyl halide, we proceed to our flow chart. So how do we determine if something is a strong or a weak base? What's our benchmark for comparison? Hydroxide, okay? And then on Monday, we drew the line a little lower than hydroxide. We added 2 additional strong bases, DBN and DBU, okay? So if the base is comparable or stronger than hydroxide, or it is DBN or DBU, then it's going to be a strong base. Everything else would be a weak base, okay? In nucleophiles, how do we decide if something is a strong nucleophile? Negative charge. And then we have our 2 exceptions. What is our neutral nucleophile that is also strong? Ammonia. And then what is our negatively charged nucleophile that is weak? terbutoxide. Okay, so we have our bulky negatively charged nucleophile that is weak, and then we have our one neutral nucleophile that is strong, ammonia. So we can make those decisions. We can decide if something is a strong base or a weak base, strong nucleophile or a weak nucleophile. So we get 4 possibilities. We can have reagents that are weak bases but strong nucleophiles. We talked about those over here and listed them in point number 1. We can have the opposite, a strong base that is a weak nucleophile. Then we can have something that is both a strong base and a strong nucleophile. And we can have species that are strong bases and, weak bases and weak nucleophiles. Okay, so we have these 4 categories. We have examples in each category. We'll start at the top. Our example for the weak base strong nucleophile is acetate. And we learned that something that is a weak base but a strong nucleophile will favor substitution because it's able to participate in SN2 reactions but not E2 reactions. So here we're going to see a lot of substitution reactions, and indeed we do. The only time we see elimination is with the tertiary alkyl halide, because that's incapable of engaging in SN2. We have to wait for the carbocation to form, and once the carbocation forms, it can either eliminate or undergo substitution. Even if it's a weak base, it will do the mixture of elimination and substitution. Okay? And because substitution is faster with less substituted alkyl halides, the reactions with the methyl or primary halides will be fast. The ones with the secondary halides will not be as fast, but they'll still occur and give us the product. Okay. Now we go down to the next category, which is opposite, strong base, weak nucleophile. That's going to favor elimination because SN2 won't be possible unless we have a methyl halide. And so we'll see E2. And indeed, we see that here. Methyl halide, we will see SN2. All other halides will see E2. And since the E2 reaction is faster with more substituted alkyl halides, the reactions of the secondary or tertiary halides will be faster than the reactions of the primary alkyl halides. Okay? Now, this third category is where we have the most possibilities if we look at this flow chart, because we're looking at reagents that are both strong bases and strong nucleophiles. So that means that both SN2 and E2 are possible. Fortunately, the rate trends are opposite. With SN2, the less substituted alkyl halides react faster. So if we have a primary alkyl halide or a methyl halide, we know it's going to be SN2 instead of E2. If it's a tertiary alkyl halide, since eliminations are faster with more substituted alkyl halides, with the tertiary alkyl halide, it will be only E2. And then where those rates intersect is in the middle with the secondary alkyl halides. And so with the secondary alkyl halide and a strong base, strong nucleophile, we would see a mixture of SN2 and E2 products. We cannot predict which would be major and which would be minor. It would depend on the specific alkyl halide, the specific nucleophile, the temperature, the solvent. It would depend on so many variables that we're not going to choose one over the other. We're just going to say that both will occur in comparable amounts. Okay? And then our last category, weak base, weak nucleophile. So here we can't have SN2, we can't have E2, so we're stuck with waiting around for the carbocation to form and undergoing SN1 or E1. What that means is that our primary and methyl halides will not react because the carbocations are too high in energy and the barrier to form them is even higher. So we only get reactions with secondary and tertiary alkyl halides. And the reaction with the tertiary alkyl halide will be slow, and the reaction with the secondary alkyl halide will be extremely slow. Okay? So that's a summary of the information in this table, this flow chart. And I don't want you to memorize this flow chart. What I'd like you to do is look at it and see if you can explain why each of these reactions gives the outcomes that are listed. Okay? When you can clearly explain the outcomes, each of the outcomes of these reactions, that's a sign that you're ready to go take the test, at least in terms of the material from chapter 7 and chapter 8. That means that you have a good understanding of the concepts of substitution and elimination. So get together with study partners, take turns explaining the outcomes, and once you're comfortable with that, then you can go take the exam. Any questions? Yes?
Why does a strong nucleophile lead to SN2, but then a strong base leads to E2? Why is that different?
So what was the first one again that you said? Strong nucleophile leads to SN2. Okay, yes? Yes, that's because those strong base, to be a strong base in a weak nucleophile, the base has to be very bulky. Because the substitution reaction, the SN2 reaction, is very sensitive to steric hindrance because you're approaching the backside of a tetrahedral carbon, then that reaction will be so slow, the only possible way for it to happen is when there's no possibility of elimination. Okay? Other questions? Yes, Minnie. Ethoxide? Ethoxide would still be a strong base because it's comparable to hydroxide. Okay, so any of the alkoxides, any conjugate base of an alcohol is going to be very similar in pKa. Although those alcohols are similar in pKa to water, so those bases have very similar basicities to hydroxide. So any alkoxide would be a strong base. Okay, other questions? All right, so let's just talk about the exam for a couple of minutes. It's going to have the same format and be the same length as exam number 1. It has 20 multiple choice questions worth 3 points each for a total of 60 points. The remaining 40 points come from 5 or 6 short answer questions. And because we've started studying reactions, we have some new types of short answer questions. We have ones where you are given starting materials and reactants, and you have to predict the products. And if stereochemistry is involved, you have to draw the stereochemistry correctly in the products. We have problems where you are given starting materials and products, and you have to list the reagents that would accomplish that reaction. And if you need more than one equivalent, as in a double dehydrohalogenation, you'd have to mention that. If it only works with a specific solvent, you would want to mention that as well. Okay, question?
Are there other cases where you would need 2 equivalents?
The only one that comes to mind is this one. So that's the one that I'm thinking of right now. There will certainly be other cases as the class goes on, but I think that's the only one we've covered so far. Yes.
If we were saying what was needed for a reaction, could we say like we need a strong base, or would we have to say
specific? So we need specific bases, specific nucleophiles, specific reagents for these reactions. Good question. And then a third type of new problem you'll see is draw the mechanism. So if we give you a reaction and then we ask you to draw the mechanism, you have to draw each step out and then you have to draw the curved arrows showing the movement of the electrons. And if you've been doing the homework, you've encountered all 3 of these types of problems, so they won't be surprises to you because we have homework problems where you have to draw mechanisms, homework problems where you have to predict products, and homework problems where you have to provide reagents. So the homework will be excellent preparation for those problems. When you're drawing the mechanisms, I just want to remind you that since a curved arrow is showing the movement of a pair of electrons, it must originate from a pair of electrons, meaning your curved arrow must originate from either a bond or a lone pair. Okay? A negative charge does not represent a specific pair of electrons, so you do not want to draw your curved arrow from a negative charge. You want to draw it from a lone pair or from a bond. And if you look closely at the mechanisms in the book, they all follow this pattern. The mechanisms we've drawn on the board all follow this pattern, where all of our curved arrows are originating either from lone pairs or from bonds. Okay. All right. Most students find this exam to be a bit more challenging than exam number one. Exam number one involved a lot of material that you'd already learned in general chemistry, and most of this material in this section is new. You want to allow yourself a little extra time. Exam one, the average elapsed time was about an hour and a half. On exam two, it's probably going to be about 15 to 20 minutes longer than that. So don't go into the testing center at the last minute. Don't be the last person to pick up a test 1 hour before the testing center closes on Friday night. That would not be a good idea. Probably give yourself 20 to 30 minutes just to be safe, more than you did for exam one. The average usually does come down a little bit on exam two relative to exam one. So if you think it's harder, if you don't do quite as well, don't be discouraged. The average usually is in the mid 70s, whereas the average on our first exam was about 80. However, there are always students who do improve from exam one to exam two. And remember, we said we would recognize those students in class next week. And so if you improve, we'll recognize you for that. Okay. Any questions? All right. Well, that's it. So don't be afraid to take it today if you're ready. Try not to take it at the last minute, and we'll see you on Friday.